welcome back to the Deep Dive. If you've been following the news at all lately, you know that drones aren't just toys anymore. I mean, they're fundamentally reshaping everything from, well, military conflict to our morning coffee run.
They really are.
And today, we're taking a deep dive into the dual reality of that technology. We've got a stack of sources here that presents, I think, the most startling contrast you could imagine.
It's true. The documents you sent over, we're talking academic research, dense engineering white papers, global market analyses. They force you to look at two worlds at once.
Right.
You have this pure, almost theoretical military speculation on one side, and then the immediate scalable engine of global commerce on the other. It's jarring.
Absolutely. And the starting point for this deep dive is pretty provocative. It's a detailed research paper that outlines a hypothetical system. 50 AI automated drones. We're talking true autonomy here, with advanced face detection, self-target locking, and a destructive payload designed to release, well, a massive amount of high energy. It really does sound like a movie script.
It does, but it's so crucial we frame this correctly. The source material is rigorous academic work.
Okay.
It's investigating the feasibility of these systems, but it explicitly emphasizes the ethical boundaries and the current real-world physics limitations, especially for those most destructive parts.
And that contrast, that's really our mission today. We're going to explore that ultimate theoretical limit of AI swarms, the stuff that kind of defies physics, and then pivot.
Right, to the foundational engineering that's required to make those swarms fly, which is where it all gets very commercially real.
Exactly. We'll get into the massive and sometimes, frankly, mundane regulatory and social walls that the commercial logistics industry is hitting right now. Things like air traffic gridlock and, simple noise ordinances.
And we'll cover how concepts like collective autonomy, decentralized computing, resilient communication, that's the shared secret sauce, really.
Secret sauce, I like that.
It powers both a future military arsenal and, the system delivering medical supplies to a remote village today. We're going to see how the software is basically ready, but the world, it might not be.
Okay, let's unpack this. We have to start with the heavy part, the philosophical and engineering question. Lethal autonomous weapons systems, or LAWs, of course. The vision that's outlined in the research is, frankly, it's chilling. It describes this coordinated strike by a collective of 50 AI-automated self-driven drones.
Right.
The idea is they can be launched from a larger mothership, say an existing military aircraft, or a specialized UAV, and then just execute a synchronized strike on a predefined area without any more human input.
And the complexity isn't just the number of units, 50. It's the sophistication of the decision-making process. The sources really highlight this precision targeting integrated with real-time face detection.
And the self-target locking. That's the key phrase.
That's the key. It means the drone, once it's deployed, it autonomously selects and tracks its own target.
And that level of delegation, that's what transforms a highly automated drone into a LogOS, right? That's the line.
Precisely. This kind of system is defined as a lethal autonomous weapons system because it crosses that line of meaningful human control. It has the independent ability to select and engage targets without an operator in the loop to validate that final strike decision.
So that power, the power to decide who lives or dies, is entirely delegated to an algorithm.
Entirely.
Okay, so here's where the hypothetical system just goes to be extreme, to the very limits of speculation. The payload. The sources talk about a destructive payload designed to release energy comparable to a nuclear weapon. Given the size and constraints of, a small drone, this is where physics just takes center stage. What are the two theoretical paths the researchers had to explore, and why, I guess, do they currently fail?
This specific element was put in the research to test the absolute boundaries of what's even possible. And it immediately highlighted these, currently insurmountable scientific barriers. They explore two paths that could yield that kind of high energy release from a small drone deployable mass.
Okay, let's start with the most famous equation in history, E mc a watt.
Right, so that's the concept of antimatter annihilation. Theoretically, it offers the absolute highest energy return for the lowest mass. The source material details that the complete annihilation of just 1 gram of matter-antimatter would yield energy equivalent to 21.5 kilotons of TNT.
21. That is in the realm of tactical nuclear devices.
It is an astonishing density of energy.
So if the physics works, why isn't this even remotely feasible today?
Well, the practical challenges are They're beyond staggering. First, just production. We can currently produce antimatter only in minute quantities, like measured in atoms,
Yeah.
and at astronomical costs. Think trillions of dollars for a single gram if we could even manage it. And then second, there's containment.
Right. It can't touch anything.
Exactly. Antimatter instantly annihilates when it touches ordinary matter. So storing a usable quantity safely on a moving, complex system like a small drone, even for a short time, involves totally unsolved engineering problems. We're talking magnetic fields and vacuum tech that's still firmly theoretical. It's confined to particle accelerators, not a battlefield.
So the second path has to be even more speculative. What's this concept of highly compressed matter?
This is sometimes discussed in relation to creating microscopic black holes. The theory involves compressing matter to such incredible densities that gravity takes over, creating a tiny black hole that then immediately begins to evaporate through what's called Hawking radiation.
And it releases its entire mass as energy.
As a burst of high-energy radiation, yeah.
And the barrier here is just the compression itself.
Yes. The sheer energy required to compress matter to these densities is nearly unimaginable. I mean, orders of magnitude beyond what any current or near-future tech platform could generate or sustain. The study is very clear on this. While the AI autonomy and the swarm coordination are active fields of research, this high-energy payload concept is purely theoretical. It faces insurmountable physics and engineering barriers.
So they contrast it with something more realistic.
They do. They contrast it with things like directed energy weapons lasers or high-power microwave systems, which are at least grounded in near-term engineering, even though they have their own massive challenges with power management and, heat.
That's a really important distinction. The drone autonomy is real. The payload is science fiction.
For now, yes.
But if we focus on just the autonomy part, the log-WS concept itself, this immediately throws us into this profound ethical and legal territory. We're talking about international humanitarian law, or IHL.
It absolutely does, and this is where the debate is most urgent. IHL mandates that militaries adhere to these core principles, like distinction, proportionality, necessity, and humanity. And distinction is key.
That's determining who is a combatant and who is a civilian.
Right, especially in a dynamic, rapidly evolving conflict zone.
And the problem is that an autonomous system just lacks the very human judgment you need to make those nuanced, context-dependent calls.
Exactly. IHL demands interpretation. Does the system recognize a combatant who is laying down their arms? Does it recognize a civilian who is using a military asset for cover? A pre-programmed algorithm struggles immensely to apply these context-sensitive principles in the fog of war.
So it could be too indiscriminate or too cautious.
Depending entirely on its training parameters. It's a huge risk either way.
And this leads directly to what legal scholars call the accountability gap.
This is the major challenge for holding individuals criminally responsible under international law. If a law commits a war crime, say it misidentifies a hospital as a military target, who is responsible? You can't put the machine in jail.
So let's unpack that. If the drone kills a non-combatant, is the responsibility with the commander who gave the high-level order to deploy the swarm?
Or is it with the programmer who wrote the opaque AI decision-making code, maybe using biased training data?
Right.
It's a distributed responsibility that our current legal frameworks just aren't equipped to handle. The commander might argue they retained meaningful human control by setting the mission parameters.
But the system's unpredictable machine actions led to the error.
Right. And the programmer might argue the system performed as intended, but the initial training data was flawed. The result is that accountability risks being diffused across this complex, opaque system. It makes a successful prosecution for war crimes almost impossible.
So the accountability gap actually lowers the threshold for bad behavior because the fear of personal legal responsibility is diminished.
It is, yeah.
And of course, the mere existence of this theoretical capability just fuels an arms race.
It's an inevitable consequence. I mean, military advancements in AI compel competing nations to develop similar capabilities. That increases proliferation risks and makes highly sophisticated weaponry more accessible globally.
And the underlying tech, the software, is easy to share.
It's dual use. The software and coordination algorithms are easy to share and adapt.
This also raises the specter of what people are calling flash wars.
Flash wars, or automated escalation. When your decision-making cycles are reduced from hours to seconds, automated systems on opposing sides can rapidly respond to each other's actions.
Creating a spiral.
An escalatory spiral that completely bypasses human review. The speed of the AI response actually reduces the human threshold for initiating or sustaining a conflict. It increases the global risk of an unintended, large-scale engagement.
So the system's designed to increase reaction speed, ironically decrease the time for human de-escalation.
Precisely.
So, okay, we start with this philosophical nightmare of longbows, but the engineering required to coordinate 50 machines autonomously is very real and very much underway. That's the pivot we need to make.
Exactly. That foundational technology is already solving problems in the commercial sphere. We shift from the question of why we shouldn't build it to how we build it for positive, non-lethal applications. And the principles of swarm resilience and coordination are the key. So the ability of a swarm to act as a single coordinated entity is rooted in these concepts of emergence and collective intelligence. It's often inspired by nature. Think of a synchronized flock of birds or a colony of ants. We define a drone swarm as a large assembly of UAVs operating together with common goals.
Okay, so if they're behaving like a flock of birds, how do they make sure that entity stays cohesive and effective?
Yeah.
Especially when, individual drones are going to fail or get damaged.
That is the essential difference between centralized and decentralized architectures. A centralized system relies on one master controller.
Which means if that one drone or ground station is compromised,
The entire mission fails. Decentralized approaches, inspired by those biological systems, are far, far superior.
and why is decentralization the preferred route?
Well, it offers superior resilience, adaptability, and scalability. It eliminates any single point of failure by intelligently distributing the computational load across the entire network. If one unit goes down, the rest immediately recalculate and redistribute its tasks.
So the computational burden, the navigation, the decision-making, the sensor processing is shared across 50 or 100 nodes.
Exactly. That distribution and shared load is the secret to resilience. It's the core advantage, built-in redundancy. This allows the swarm to cope gracefully with the loss of individual units.
Instead of failing, it just adapts.
Right, the swarm exhibits emergent behavior. Simple, local rules like maintain distance from your neighbor, move toward the goal, result in sophisticated, complex collective behaviors. That ensures mission continuity even under degradation.
This reliance on collective action requires rapid, reliable communication, which brings us back to that massive bandwidth problem. Managing telemetry for 100 rapidly moving aircraft in a dynamic airspace must just overwhelm traditional networks.
Oh, it creates a formidable challenge. Standard internet protocols, things like TCP/IP, they perform really poorly in the lossy, wireless environments that are common to drone formations.
Because they're designed for stable wired connections.
Exactly. And they panic. They try to reestablish the connection and resend data constantly every time a drone briefly loses signal or moves behind a building. And this just creates massive lag.
So what are the radical approaches researchers are using to deal with that gridlock?
They require what's called disruption-tolerant networking, or DTM protocols. These are engineered specifically to anticipate and tolerate frequent loss and reestablishment of connections.
So it's like being patient with bad cell service.
That's a great way to put it. If you and a group of friends are walking through a zone with patchy cell service, you don't panic and redial every time the signal drops. You assume you'll reconnect soon, you hold the message, and you send it when the connection stabilizes.
It makes the system patient and persistent.
Exactly. So protocols like DSDV, AODV, and OLSSR are crucial here. They're designed for mobile ad hoc networks, or MANETs, which are networks without any fixed infrastructure. It allows the drones to communicate seamlessly, even if they lose sight of the central command post.
Our sources also touched on a specialized conceptual framework, the swarm protocol, which adds advanced security features.
Right. The conceptual swarm protocol is all about layered resilience and security. It's designed for high-stakes environments. A key feature is its adaptive encryption.
What does that mean, adaptive?
It means it uses high-grade standards like AES for extremely sensitive mission data, but it can automatically switch to faster, less CPU-intensive encryption like FIRNet for less critical telemetry. It adjusts the data protection based on the conditions and the threat level.
And what about interference or outright jamming? Especially if these swarms are operating in areas with high radio frequency traffic, like our cities.
This is where redundancy in the transmission channels is vital. The swarm protocol supports simultaneous data transmission across multiple diverse channels.
So not just radio.
Not just RF, we're talking RF, Wi-Fi, Li-Fi, which is
Uh-huh.
communication using light and optical links. It has an automatic channel switching mechanism to bypass localized interference or jamming. If RF is blocked, it just seamlessly switches to Li-Fi or an optical link, ensuring a continuous data flow.
And the really clever technique for avoiding detection or jamming in a city, that frequency hopping spread spectrum, how does that work in practice?
FHSS is an incredible technique for security and signal integrity. Instead of transmitting on just one frequency, the system rapidly switches. It hops across dozens or hundreds of frequencies many times per second. And it does this according to a predefined but pseudo-random sequence.
So what does that look like to an opponent trying to jam the signal?
To an enemy trying to intercept or jam it, it's like trying to catch a mosquito that jumps channels every millisecond. The jammer has to transmit noise across the entire spectrum at once, which is highly power intensive.
Or they just fail.
Or they only succeed in disrupting tiny, momentary segments of the transmission, making the overall message virtually impossible to block entirely. It dramatically increases data security and minimizes crosstalk in dense RF environments.
So all these protocols ensure the data gets through. But the final challenge for collective intelligence is making sure all 50 drones agree on the next move at the same time, even if you're cut off from command.
Right, that requires decision consistency, and that relies on something called distributed consensus algorithms. The sources mention the RAFT algorithm. This is fundamental for enabling the drones to make collective decisions and coordinate actions autonomously.
How does a consensus algorithm like RAFT work in a fleet of moving drones? Is it like a constant vote?
It's exactly like a highly efficient instantaneous voting system,
Yep.
or a shared ledger. The drones have to agree on the order of actions, who's the leader, what's the next task, how do we route around a sudden obstacle, and that agreement must be finalized immediately.
And RAFT ensures that happens even if the ground link is lost.
Yes. If the link is lost, the swarm can autonomously elect a new leader and continue executing the mission plan based on that agreed-upon state. This capability is critical, whether you're coordinating a search and rescue pattern or a dynamic reroute for a complex delivery.
So communication is the nervous system. The eyes and brain of the swarm are the autonomous navigation and perception. How does an individual drone get a robust understanding of a complex, dynamic, real-world environment?
This is the triumph of sensor fusion. No single sensor is robust enough. A monocular camera suffers from distance errors, millimeter wave radar can be poor at fine-grained classification, and IMU's inertial measurement units, they drift over time.
So you have to combine them.
Sensor fusion is paramount. You combine data from multiple diverse sensors cameras, radar, LiDAR, IMU, RGBD cameras, to enhance reliability and robustness across all kinds of conditions.
Can you give us a concrete example of that fusion, providing a capability that a single sensor couldn't?
Sure. Take obstacle avoidance in poor visibility, like fog. A single camera might struggle, but the system fuses that camera data with millimeter wave radar data to extract precise 3D coordinates of obstacles regardless of the light.
Oh.
Or it can integrate IMU data, which tells it its current speed and acceleration, with RGBD camera data, which provides depth perception, to accurately predict the trajectory of a moving obstacle, say another drone or a bird. That ensures any evasive action is timely and accurate.
And the intelligence behind the navigation itself, the ability to maneuver without a predefined map, that must require a constant process of learning.
That's where deep reinforcement learning, or DRL, comes in. DRL allows drones to learn from iterative trial and error. It enables them to navigate highly complex, unknown environments without relying on pre-programmed routes or detailed maps.
So they're basically rewarded for successful navigation.
Precisely. They're trained by receiving a reward signal for successful actions, like reaching a waypoint or efficiently avoiding a collision, and a penalty signal for failures. Over countless trials, both simulated and real-world, they continuously refine their navigation policy until the AI can handle novel situations robustly. This is what gives the swarm its adaptability.
And finally, circling back to that hypothetical Lotto B system, the capability for self-target locking and precision targeting integrated with real-time face detection requires another layer of AI.
That is the Target Acquisition, Tracking, and Locking Module, or ATL. This uses sophisticated AI tracking algorithms, often based on neural networks, combined with what's called guidance rate technology. For a moving target, the drone has to continuously calculate the relative position and velocity many times per second to ensure the lock is maintained and the trajectory is accurate.
And I imagine ATL relies heavily on that same multi-sensor fusion we just discussed.
Absolutely. The accuracy required for precision targeting can't rely on a single input. ATL modules merge data from high-res optical cameras, LiDAR for range finding, and thermal sensors. This multimodal input increases the probability of correctly identifying and estimating the position of the target.
Whether that target is a person, a piece of equipment, or a vehicle.
Exactly. The technology itself is agnostic. It's the application that determines the outcome.
And that's the key takeaway from the engineering side. The resilient communication, the decentralized coordination, the multi-sensor AI perception, all of it is dual use. And now we see these technologies driving explosive, immediate market growth in the commercial sector. So we're transitioning now from the lab bench and the drawing board to the economic reality. If military concepts are pushing theoretical physics, the commercial sector is pushing the boundaries of global infrastructure and scale. Let's talk about the size of this economic wave.
The numbers are staggering. The global AI and logistics market was valued at about $26.3 billion just a few years ago in 2025. But the projected growth is exponential. It's expected to reach nearly $708 billion by 2034.
Wait, from 26 billion to 708 billion. That's a compound annual growth rate of 44% over that forecast period.
It is. And it's fueled by quick commerce, online shopping, and automated warehouse management. That growth rate alone tells you how foundational this technology is becoming.
It's not a niche anymore.
Not at all. And we're already seeing the results among early adopters. Companies that successfully integrate AI-enabled supply chain management are reporting massive efficiency gains. The data shows reports of a 15% reduction in logistics costs, a 35% reduction in inventory levels, and a 65% improvement in overall service levels.
So a drone isn't just replacing a delivery driver, it's reshaping the entire economics of delivery.
That's right.
Okay, let's break down the cargo drone spectrum. Let's start with the small, last-mile systems that are delivering food and pharmaceuticals today.
These are the quick delivery specialists. They're often multi-rotors designed for short, rapid, high-frequency deliveries. Alphabet's Wing is a prime example. They're operating in suburban and semi-urban environments. Their drones can handle a payload of about 5 pounds, fly at speeds up to 65 miles per hour, and they've secured major partnerships with retailers like Walmart and DoorDash. That signals their intent for true mass market expansion.
And then there's Zipline, which has achieved incredible scale, especially in the humanitarian and healthcare space.
Zipline is the global benchmark for high-volume operations. They hold about 21.5% of the medical drone delivery market share today. Their P2 system carries about an 8-pound payload and delivers at 70 miles per hour.
But the defining stat is the volume, right?
It's the volume. They have completed over 1.4 million deliveries globally. That number alone demonstrates that the technology is robust, reliable, and deployable at scale. They're often providing blood, vaccines, and crucial pharmaceuticals to remote, inaccessible regions where road infrastructure is poor or non-existent.
But last-mile delivery only gets the package from the distribution center to the door. For the real logistical revolution, we need heavy-lift, long-haul platforms that can truly disrupt the air freight industry.
And that shifts our focus to fixed-wing platforms like Dynamics Black Swan. This isn't a small multi-rotor. This is designed to be a disruptive middle and long-mile cargo solution. The critical stats here are huge.
Oh, huge.
It can carry 350 kilograms, that's 770 pounds, over 2,500 kilometers, or 1,550 miles.
770 pounds. That's the weight of a small car. That capacity immediately changes the conversation from delivering a burrito to delivering, I don't know, specialized manufacturing components or huge quantities of produce.
And its business model is centered on transforming access. The Black Swan is designed to operate from smaller regional airports and airfields. There are over 4,000 of these currently underutilized regional hubs in Europe alone, which are too small for conventional aircraft.
So it bypasses the big, congested central hubs.
Exactly. By making air freight cheaper and accessible at these local points, it radically cuts transport times and costs for small and medium-sized businesses and isolated communities.
The theoretical engineering is clearly working, and the economic projections are huge. Let's look at how these technologies are being actively integrated into real urban environments globally. Let's start with the U.S. urban mobility pilots.
A fantastic case study is the Aerialoop pilot in Detroit within Michigan Central's Advanced Aerial Innovation Region, or AAR. This project uses an FAA-cleared beyond visual line of sight BVLOS route to transport lightweight prototype parts between manufacturing sites. It's only a short 1-mile route, but it's operating in a highly complex, real urban setting.
And what was the primary benefit they saw in that Corktown neighborhood of Detroit?
The primary benefit was efficiency and environmental gain. The pilot proved that transporting that cargo by drone was 5 times more energy efficient than using traditional road transport. They've successfully completed over 600 cargo flights between properties. This demonstrates the viability of middle-mile drone operations, where speed and efficiency in moving materials within a corporate campus are paramount.
Europe, on the other hand, seems to be using public service applications to build regulatory frameworks and public trust at the same time.
That's the strategy. Prove safety and value. The UK, for instance, has several prominent initiatives. Scotland's CALS program, backed by NHS Scotland, has conducted extensive live trials moving lab samples and medicines between hospitals.
And the key outcome is time, I assume.
It's all about time reduction, cutting journey times from hours if you're relying on ground transport stuck in traffic to just minutes. This demonstrable efficiency and proven safety record in a healthcare setting is crucial for easing public acceptance of these BVLS operations.
And we're seeing much larger managed corridors being implemented at a national scale in Asia and the Middle East.
Absolutely. Look at China's low-altitude logistics corridor initiative, deployed across 5 major pilot cities, including Chengdu and Shenzhen. This project is integrating 5G-based unmanned traffic management, or UTM, and deploying 3 specialized drone swarm types at the same time.
What are the 3 types?
You've got large delivery swarms for hub-to-hub transport. That's about 15% of the deployment. Then medium multi-rotor swarms for last-mile delivery. That's the bulk at 60%. And then micro-monitoring drones making up the last 25%, providing real-time situational awareness.
And what were the operational benefits in the Shenzhen pilot zone?
The system achieved an incredible daily throughput of 1,200 orders in that pilot zone. And more importantly for the business case, it generated a 38% reduction in operational costs compared to traditional delivery methods. This is where you see the convergence of swarm engineering and logistics, high volume, high efficiency, and integrated management.
And Israel is moving even further toward a fully automated managed airspace with the INDI-3 initiative.
INDI-3 is a powerful example of what's coming globally. It's a national-scale deployment managed by Airways' AI-driven dynamic UTM system. This system basically acts as the air traffic controller for everyone.
Everyone.
Municipal services, security, emergency responders, and commercial logistics, all operating simultaneously in the same low-altitude corridors.
How fast does an AI system have to be to manage that kind of complex traffic?
It has to be almost instantaneous. The system continuously monitors for all manned and unmanned aircraft, making autonomous decisions like flight validation, deconfliction, and route suggestions within a mere 5-second window. It's the central orchestrator that prevents conflicts and lets multiple operators safely share the same airspace in real time.
Beyond pure commercial profit, the humanitarian applications of AI swarms are maybe the most compelling argument for this technology.
It's the life-saving side of the coin. The primary advantage in disaster response is raw speed. When infrastructure is compromised, damage assessments that traditionally require days for ground surveys can be completed in minutes. The sources cite the Chloroquy system, which is capable of assessing damage to 2,000 homes in just 7 minutes.
7 minutes. That speed saves lives.
It does. And these autonomous systems manage to achieve such rapid, accurate assessments using advanced, specialized AI. For wildfire management, thermal sensors are used to detect subsurface hotspots and predict spread patterns, feeding that data immediately to fire crews.
And for search and rescue.
In search and rescue, neural networks, which have been trained on vast disaster datasets, classify debris types, and, crucially, identify human heat signatures with remarkably high accuracy, reported to be between 85% and 95%.
And the swarm technology ensures that coverage remains resilient even when traditional communication lines are down.
That decentralized coordination is critical. When ground communication infrastructure fails, the swarm coordinates autonomously using those DTN protocols we discussed earlier. They provide simultaneous multi-area coverage, eliminating the sequential, time-consuming inspections common with traditional methods. This real-time adaptability is absolutely crucial for accelerating life-saving interventions during a crisis. The path to scaling these commercial and humanitarian applications is fascinating because the biggest hurdles aren't the high-level AI algorithms anymore. They're the mundane, physical, or bureaucratic challenges: noise, endurance, air traffic law, and public perception.
Let's start with that pervasive, seemingly simple barrier to urban usage: noise. If you want a fleet of heavy-lift drones operating over a city, you run headfirst into urban noise regulations.
It is a major impediment to last-mile delivery scalability. The constant buzzing is an annoyance that just erodes public acceptance. But this is where elegant engineering provides a solution. I find this detail particularly exciting. The toroidal propeller developed by MIT Lincoln Laboratory.
The one with that unusual closed-loop, almost woven geometric shape.
Exactly. It's a radical redesign of the traditional propeller. The noise from a propeller is primarily generated at the leading and trailing edges of the blade. The toroidal design is a closed loop that omits that harsh leading edge entirely, where the noise is generated.
So it cuts out the noisiest part of the blade.
And this innovation decreases the signals in the frequency range to which the human ear is most sensitive.
That sounds like a brilliant, almost deceptively simple solution. What were the performance metrics from the research on this design?
The results were phenomenal. At the same thrust level needed for a drone to hover or move, the toroidal propeller increased the lift coefficient by a massive 187% compared to a conventional propeller.
Wow.
But the real game changer for urban adoption was the acoustic signature. It decreased the radial sound pressure levels by 5.2 dBA, and even more critically, it decreased the axial sound pressure levels, that's the sound directed straight down toward the ground, by a whopping 19.6 dBA.
Nearly 20 dBA reduction in the sound profile directed at the people below. That is the difference between an irritating buzz and something that just fades into the background noise. That could unlock urban air mobility.
It's an essential engineering fix that addresses a social barrier without adding weight or requiring supplementary power. It's a perfect example of hardware design overcoming social friction.
Beyond noise, scaling commercial fleets means optimizing hardware for long-term endurance and resilience to physical damage.
Structural integrity is key. We're moving beyond standard carbon fiber and aluminum alloys, which are used for their strength-to-weight ratio, into more exotic territory. The push is for self-healing composites.
Self-healing, like the drone has its own immune system.
Precisely. It's like the drone has its own clotting factor built into the airframe. These materials are designed with these tiny microcapsules containing a healing agent. If a small crack or flaw forms due to impact or stress, the microcapsules rupture, they release the agent, which then autonomously fills and seals the flaw. It extends the operational lifespan and safety of the drone without human intervention.
And of course, the energy limit remains the operational bottleneck. It restricts flight time and payload capacity.
It does. While lithium-ion and lithium polymer batteries are ubiquitous, the industry is heavily investing in novel energy storage. Solid-state batteries promise significantly higher energy density, potentially double the power storage, and they're inherently safer than liquid electrolyte batteries.
And for the heavy lift, long-endurance platforms like the Black Swan.
For those, hydrogen fuel cells are the ultimate goal. They offer superior energy density for flight times measured in hours rather than minutes.
So if the engineers can solve noise, resilience, and power, the next massive wall is regulatory. Beyond visual line of sight, or BVLOS.
BVLOS is the holy grail for logistics. If you can only fly a drone as far as the operator can see it, you can't scale a delivery network. But flying beyond sight means integrating drones into the existing national airspace, which fundamentally alters right-of-way rules and requires sophisticated automated traffic management.
So how is the U.S. FAA handling the normalization of BVLOS operations?
The U.S. is progressing, but it's a slow, meticulous process. The FAA released a notice of proposed rulemaking for normalizing BVLOS operations, introducing new Parts 108 and 146. This is the necessary bureaucratic foundation, but the speed of approval for widespread commercial deployment remains a major constraint compared to other regions.
How are Europe and the U.K. comparing in terms of readiness?
Europe has established the U-Space Framework, which is a comprehensive regulatory suite of services designed to enable high-volume drone operations across the continent. Those rules formally took effect in January 2023, providing a clear, unified structure for commercial operators to follow.
And the UK has a very specific timeline for urban air mobility.
Yes. The UK's Civil Aviation Authority uses the Specific Operations Risk Assessment, or SORAR, framework. They've established 3 clear operational pathways. Crucially, the low-level urban BVLOS path, which is what you need for last-mile delivery across cities, is aggressively targeted for deployment by 2028 or 2029.
That gives the industry a firm goal to plan toward.
An ambitious one, but yes.
As more drones populate these sky delivery drones, inspection drones, public service drones, the need for robust counter-unmanned aircraft systems, or CUAS, becomes critical for safety and security.
CUAS capability isn't optional. It's an essential layer of security, particularly in dense, urban, high-traffic environments. R&D in this space is intense, focused largely on detecting and mitigating micro and mini UAS, as you can see from major initiatives like the Canadian CUAS Sandbox 2025.
What kind of technical diversity are we seeing in these counter-drone solutions?
They're highly integrated and multimodal. They use deep data fusion, combining traditional radar, acoustic sensors, and optical sensors. And crucially, we see the integration of advanced cognitive electronic warfare systems, C2EWS, which are specifically optimized to defeat swarms.
So they don't just jam one drone.
No, they autonomously track, identify, and disrupt the swarm's coordination and communication protocols.
But not all drones rely on radio communication, which presents a unique challenge for these jamming systems.
That's right, and this is why non-RF detection is so vital. We have to consider threats like tethered drones, which can use a fiber optic cable up to 30 kilometers long for control and data transmission.
Wait, a fiber optic tether. So if the control signal is running through a physical line, why can't we just jam it?
Because there's no radio frequency to jam. Electronic warfare systems rely on disrupting the radio link between the drone and the operator. If the data is being transmitted via light through a physical cable, electronic jamming is useless.
So you need passive detection systems.
Exactly. Things like advanced acoustic analysis or high-resolution optical tracking to identify and neutralize the threat, which is much, much more difficult in a noisy urban environment.
And finally, the last challenge, and the one that links the military surveillance theory right back to the commercial reality, is the crisis of privacy and transparency.
This is arguably the single biggest non-technical hurdle to BVLOS expansion and achieving widespread public acceptance. The fundamental truth is that drones are incredibly powerful aerial surveillance platforms. And BVLOS operations enable them to fly longer, farther, and carry increasingly diverse and sophisticated surveillance payloads, dramatically increasing the risk to public privacy.
And our sources highlight that the U.S. is currently ill-equipped to handle this risk legally.
That is correct. Case law surrounding aerial surveillance of public spaces remains murky. Existing state consumer privacy laws are largely ineffective because they're often based on weak notice and consent regimes.
Right, a company can just post a notice saying they're recording.
And that doesn't meaningfully limit the volume, nature, or duration of the data collected over public or even private areas.
And if the public fears this intrusion, it limits commercial opportunity.
Precisely. The FAA itself has noted this danger. They stated, if people don't feel safe when drones are operating around them or they have persistent fears of drones intruding in their private lives, then UAS commercial opportunities will be very limited. Public backlash translates directly into legislative restrictions and local community resistance, which slows BVLOS rollouts.
So transparency is becoming a core demand from advocates. What specifically are they calling for?
They're demanding mandatory transparency measures from regulators and operators. This includes transparency around drone incidents, crashes, losses of control, system failures. They also demand transparency regarding automated data service providers, the companies running the UTM systems, who gain this privileged access to flight data.
So if private companies control this global bird's-eye view of all flight activity, the public needs to know how that data is being used.
It's protected, yes.
And critically, a voice for local communities.
Absolutely. The current proposed FAA rules contain no provisions for local community input into BVLOS operations over their streets and their homes. In a democracy, the argument is that local residents must have a say over the establishment of a new, persistent aerial layer of traffic and surveillance. Without that community buy-in, widespread commercial operation is just not feasible.
So we started this deep dive in the realm of science fiction, looking at lethal autonomous weapon systems that required science to, defy physics to achieve their most extreme potential. And we end in the world of logistics and healthcare, where the biggest breakthroughs required are not in physics, but in regulation and sociology.
The tension is clear. The underlying technological spine, the decentralized AI autonomy, the self-healing composites, the multi-sensor fusion, the resilient collective coordination, it's shared. It's advancing rapidly across military and commercial sectors globally. The difference between an autonomous weapon system that chooses its target and an autonomous medical delivery network is often just the payload and the operational context.
So the core takeaway for you, the listener, is that the future of drone swarms isn't being determined solely by engineering brilliance. That part is a constant. It's being determined by whether policymakers can successfully create an equitable, safe, and transparent regulatory environment before public acceptance just erodes completely.
And this brings us back to the stark reality of the dual-use dilemma. The very design elements that make a drone swarm resilient enough to coordinate a military action, its collective intelligence and rapid autonomy, are the exact same elements that allow a fleet to deliver crucial medical supplies to a remote village, or assess the damage of a wildfire in minutes when human intervention is impossible.
Right.
The question for policymakers and for you as a citizen watching this revolution unfold is not how to stop the technology, but how to control the application and ethical deployment of its inevitable convergence. It's a challenge of intent, not just engineering.